In the last video, we saw how to use slope fields or direction fields to visualize the general solution for a differential equation. We have to have differential equations that are first order, where y prime is a function of x and y. So we practiced trying to draw some of these slope fields by hand, and then we saw how to use Desmos to generate the slope fields for us. Let's work through a couple more examples trying to understand the relationship between the slope field picture and the differential equation that generates it. So for example 2, we want to match each of these differential equations to the different slope fields that are given below. So let's just look at these differential equations here and look at the form. We have y prime equals for each one of them, or we could also call this dy over dx. And notice that in each case, we have solved for y prime on one side, and it's equal to an expression in terms of x and y. So this first one is actually just in terms of x. This one's just in terms of y. This third one's just in terms of x. Some of them have x's and y's, but these are all of the proper form. We have the derivative equal to some function or some expression in terms of x and y. So all of these satisfy the correct form. This first one, what is the name for this sort of a differential equation where the derivative only depends on y? This is autonomous. So this is an autonomous differential equation. The derivative only depends on y. We saw an example of that earlier. This particular example, example 1, we had an autonomous differential equation because 2 over y is only a function of y. And we noticed that any horizontal line has all the same slopes across it. So this will always be true. If the differential equation only depends on y, if it's autonomous, then along any horizontal line we have the same y value, so the slopes will all be the same. The x value does not influence the value of the slope. So for this differential equation, we're looking for a slope field where the slopes are all the same across horizontal lines. How about this one right here, where y prime equals x? We have sort of the opposite behavior here. If y prime equals x, then the derivative does not depend on the y values, only on the x values. So for y prime equals x, we're looking for a slope field where the slopes are all the same along vertical lines. Okay, so y prime equals y. Look at these different slope fields and see which one has the same slopes across horizontal lines. That's going to be this one here. We have the same slopes if we look at any particular horizontal line. The slopes along those horizontal lines are always the same. So that will be the answer for this first one, y prime equals y. So this graph right here, this corresponds to A. Let's think also of how this is generated. This differential equation says that the derivative always equals the y value. So if we choose a certain y value here, let's just say this point right here. The y value is 5. If the derivative is 5, that means the slope here is 5. So all of these lines have a slope of 5. If we choose y equals 0, notice how we have horizontal tangent lines, slopes of 0. Y equals -1, we always have a slope of -1 because in this case, the slope of the differential equation equals the y value itself. Now we saw this example in an earlier video, and the solution to this differential equation is the exponential function, y equals c times e to the x. And if we were to plot any particular solution in this slope field, let's just choose a point here. If we plot a solution passing through this point, we would match up with the slopes of the slope field, so it would look something like this. And notice how that looks like an exponential function. So the solutions here are exponential functions. This graph corresponds to y prime equals y. Let's take a look at part C here, y prime equals x. Here the derivative does not depend on y, it only depends on x. So if we were to look at a vertical line, the different y values would not influence the slope. So the slopes should all be the same along a vertical line. Which graph or which slope field satisfies that? Well, it can't be this one. I have different slopes along that line. I have different slopes for this one along that line. It's this graph right here. If I look at any vertical line, the slopes are always the same. This is not autonomous. It's sort of the opposite of autonomous, where the derivative only depends on x. So this plot corresponds to C, y prime equals x. We can actually solve this differential equation. If y prime equals x, well, to solve for y, we would just take the antiderivative of x. So here, if we find the solution, this is the differential equation. If we take the solution, we just integrate x. So the solution would be y equals x squared divided by 2 plus c. So this is about the simplest sort of differential equation, where the differential equation is only a function of x, then we can simply integrate. Again, this method will not work in general. It only works when y prime equals some function just of x. But here's the solution. And notice this, x squared divided by 2. These are parabolas that are stretched, or actually squished by a factor of 2. And we can add plus c. So the shapes that we get if we follow the slope field are these parabolas. This would be x squared over 2 plus 0. X squared over 2 minus 5 would be this one right here. All of these different shapes, if we follow the slope field, are parabolas. Let's take a look at these other two differential equations that we haven't yet matched. And we won't talk about the solutions for either of these. For part D, we'll see a method later on to find the solution, but we're not interested in finding the solutions here. Take a look at this differential equation. It's either going to be this graph or this one. How do we figure out which one matches? Well, one way to do it is to take sample points and plug them into this differential equation. So let's start at the origin. If we plug in the point for the origin, we have 0 minus 0 times 1/2, so we have 0. And it looks like we don't have, well, it's kind of hard to tell. Do we actually have horizontal lines here, or it seems to be sort of missing. But if we look at this other graph, at the point 0, 0, we have a horizontal tangent line. For this differential equation, y prime is undefined at 0, 0. So this part B has to correspond to this slope field. So this is B. And let's just think about how that slope field matches the differential equation. So this is the differential equation y prime equals 1/2 times x minus y. If we take any points in the xy plane and plug them in, we should get the different slopes that we see in this slope field. So let's think of any point along the line y equals x. If we take the line y equals x, then the x and y values would cancel out and we get slopes of 0. And notice how these slopes are always 0 along the line y equals x. So that matches what we'd expect from this differential equation. If x is larger than y, then we would expect positive slopes. So here, x is larger than y in this region here, and we have positive slopes everywhere in this region. If y is larger than x, then x minus y would be negative, so we'd have negative slopes. Y is larger than x in this region here, so notice that all of the slopes in that region are negative because y is larger than x. So this differential equation matches the slope field that we see here. So the only one left by process of elimination, we've taken care of this one, and this one. This slope field must correspond to x over y. And let's talk a little bit more in depth about how this differential equation describes the slope field. So we have y prime equals x divided by y. First of all, notice that if x and y are the same, then x divided by y is just 1. And x and y are the same when y equals x, that's this line right here. So along this line, the slope is always 1. That matches what we would expect. When y equals 0, we don't see any lines for the slope field. They would actually be vertical lines here. But when y equals 0, we have an undefined slope, so that matches what we see in the picture here. How about the line y equals negative x? Along this line, y equals negative x. If we do x over y, we would have negative 1. That's why the slopes that we see here are all negative 1. If x is larger than y, then we will see slopes greater than 1. So we see that sort of behavior in here, if x is larger than y. If y is larger than x, then we'll see slopes less than 1. So we see that all in here, where y is larger than x. If either x or y are negative, we would have negative slopes. If both x and y are negative, then we have positive slopes. So if we have negative over negative, that happens in this quadrant, all the slopes are positive. If x and y are both positive, then we always have positive slopes. If one or the other of x or y are negative, then we have negative slopes. That's what we see in quadrants 2 and in quadrant 4. So hopefully you can see how this slope field matches up with this differential equation. We could plot more specific points here. We could take, say, let's just take this point right here. This is the point 5, 6, 7, 3. So if we take the point 7, 3, x is 7, y is 3, we'd have 7/3 for the slope. And that looks like, sure, about 7/3. So we could take different specific values, plug them into the differential equation, and we would see that the slopes here always match up with x divided by y. So this slope field is letter D. Take a look at the next example. what we'd like to do for each of these direction fields is plot the solution curve passing through the point 0, 2. This is an initial condition. We could also say that this is y of 0 equals 2. That's another way to phrase this initial condition. And for each of these different slope fields, we want to take the point 0, 2 and sketch the curve that passes through that point. So 0, 2, that's right here. And for this differential equation, I go with the flow. I try to match the way that the lines point me. So I start going this way, and then I start moving up a little bit, something like that. So I'll go ahead and draw that in. And then I can also go in the negative x direction. The slope field is pointing me this direction. I want to follow parallel to the slope field lines. So it would look something like that. So here is this solution passing through the point 0, 2. Let's do the same thing for this next picture. Right here is 0, 2. By the way, the actual specific solution would be y equals 2e to the x. That's actually the graph that we're going to see here. So follow the slope field lines, and it looks something like this. There's the graph of the function y equals 2e to the x. That's the specific solution passing through the point 0, 2. How about the next ones here? 0, 2 is right here, and we get this parabola. Once again, I'm trying to sketch a curve that is always parallel to the slope field lines. It doesn't have to be super precise, but it needs to roughly follow the slope field lines. I wouldn't want to draw something that goes against the grain here. I need to go with the flow. Now, this parabola is y equals x squared over 2 plus 2. So that's the specific solution, y equals x squared over 2 plus 2. Finally, for this last slope field, here's the point 0, 2. We want to sketch the solution curve passing through that point. And this looks something like this. Now we have one more example here to do. For each of these direction fields, we want to plot the solution curves satisfying this equation. What is this? This is an initial condition. So we have an initial condition here. And remember that when we have a differential equation along with an initial condition, this is called an initial value problem. We're getting specific solutions to the differential equation. So we want the specific solution satisfying y of negative 5 equals negative 5. So in other words, these are passing through the point negative 5, negative 5. That's another way of phrasing this. So we're going to look at the point negative 5 for each of these slope fields and plot the curve passing through that point. At this point, I highly encourage you to pause the video, and for each of these different examples, look at the point negative 5, plot the solution curve for each of these 4 slope fields. So take a minute to do that, and then we'll come back and we'll work through it together. So for this first differential equation, here's negative 5. I want to plot the line, or the curve, that follows this slope field lines. And it looks like, well, this is just going straight this way, and it just keeps going like this. So it looks like y equals x is actually a solution to the differential equation. Now let's explore that a little bit further. This is the line y equals x. It's a specific solution, and apparently y equals x is one of the solutions to this differential equation. Let's actually work through the steps to verify that that's true. If y equals x, this is what we're seeing as a solution. That's not the general solution, it's just a specific particular solution. But let's verify that this actually does work as a solution to the differential equation. So if y equals x, then y prime equals 1. And I'd like to look at both sides now of the differential equation. So y prime equals 1, and then y over x, or rather x over y. Well, if x equals y, then I could write that as y over y. That's 1. So notice that y prime equals 1, x over y equals 1, so x over y equals y prime. Therefore, y equals x is a valid solution to this differential equation, as we can see from the slope field here. Okay, next example here. Let's plot the specific solution passing through negative 5. There it is. And if we follow the slope field lines, it'll look something like this. Let's complete the curves for the next two as well. Negative 5, that's right about here. So we follow the flow of the slope field lines. Looks like we kind of go off the screen a little bit here. and should look maybe something like this. We don't have to have, again, a super precise picture. It just needs to roughly follow the direction field lines. Finally, -5 for this one. We have -5 right there. Notice that we have a horizontal tangent line here. We might be kind of tempted just to draw a horizontal line here. But we can't just continue with a horizontal line because it's not going parallel to these slope field lines. So it's going to start horizontal, and then it's going to slowly curve upward like this. So this graph would look something like this. And then in this direction, following the slope field lines, something roughly like that. So once again, slope fields are visualizations of different solutions for differential equations. We have to have differential equations in the proper form, where the derivative dy dx is a function of x and y, and each one of these differential equations has that sort of a form. And if we follow the slope field lines starting at any point, we will get a different solution to the differential equation. Slope fields help us to visualize all of the solutions for a differential equation.